Hello everyone, my name is Svetlana Minakova and I'm a PhD student of Leiden University, located in the Netherlands. I'm performing research in fields of deep learning and embedded systems. My research is conducted as a part of a European project called ALOA. In this video, I am going to present my research paper called Combining Task and Data Level Parallelism for High-Throughput CNN Inference on Embedded CPUs-GPUs MPSoCs. In this paper, my co-authors and me propose a novel methodology for efficient execution of convolutional neural networks on embedded MPSoCs. As you can hear, my topic sounds pretty complicated, and therefore I would like to start with some background necessary for understanding of the proposed methodology. On this slide, you can see a convolutional neural network. Convolutional neural networks, or CNNs, are powerful biologically inspired computational models, typically represented as graphs with a set of nodes called layers and a set of edges, representing data dependencies between the layers. Due to their ability to handle large unstructured data, convolutional neural networks had become dominant in various computer vision and natural language processing tasks, and nowadays are at the core of many applications. Due to their high complexity, state-of-the-art convolutional neural networks are typically executed on high-performance platforms and provided to edge devices, such as mobile phones, tablets, or cameras, as cloud services. However, some of the applications require execution of the CNNs right on the edge devices. One of the main reasons for execution at the edge is high latency, occurring due to communication of an end device with the server in case of the cloud applications. The low latency is unacceptable for CNN-based applications that require real-time response running in self-driving cars or drones. However, execution of CNNs on embedded devices can be challenging. While applications provided as cloud services have virtually unlimited computational resources, the resources of embedded devices are very limited. Therefore, execution of CNNs on embedded devices requires special techniques that would allow efficient utilization of limited embedded device resources. Many modern embedded devices are based on embedded CPUs-GPUs multiprocessor systems on chip, MPSoCs, complex integrated circuits that consist of processing elements with specific functionalities. Due to their specific design, MPSoCs offer energy-efficient and high-performance solutions for applications running on the embedded devices. The computational resources available in the CPUs-GPUs MPSoCs are distributed over the heterogeneous MPSoC processors, CPUs and GPUs. To ensure high-throughput execution of a CNN on an embedded CPUs-GPUs MPSoC, the CNN workload should be efficiently distributed among the processors available in the MPSoC. To efficiently distribute CNN workload over the MPSoC processors, one should efficiently exploit the parallelism available within the CNN. There are two types of parallelism available within the CNN. The first type is data-level parallelism. This type of parallelism is available within CNN layers. It involves the same computation, for example max pooling, performed over partitions of the layer input data. On this slide, you can see an example where a max pooling CNN layer processes its input data in 4 parts. If an embedded MPSoC has enough resources, all 4 data parts can be processed in parallel. Parallel execution of data parts allows to speed up individual CNN layers computation and achieve high CNN throughput. Another type of parallelism available in a CNN is the task-level parallelism. It involves execution of several CNN layers in parallel pipelined fashion. The pipeline parallelism is related to the streaming nature of CNN applications, where input data comes as a stream of input frames. As shown on this slide, with several processors available in the platform, several CNN layers can be executed in parallel if they perform computations over different input frames. Exploitation of task-level parallelism allows to speed up the overall CNN computation. The existing approaches typically utilize only one type of parallelism. Some approaches utilize only task-level parallelism by distribution and pipelined execution of CNN layers on the MPSoC CPUs. However, these approaches do not utilize embedded GPUs to speed up the computations within CNN layers and typically do not achieve very high throughput. Other approaches utilize only data-level parallelism. In these approaches, highly parallel computations within CNN layers are offloaded for computation on embedded GPUs. However, the embedded CPUs are utilized only for communication with GPUs and most of the time remain idle. This means that embedded CPUs are not efficiently utilized, while utilization of embedded CPUs and pipeline parallelism would allow further improvement of CNN throughput achieved by exploitation of data-level parallelism. In our methodology, we propose to utilize both task-level and data-level parallelism for efficient execution of CNNs on embedded platforms. In our approach, CNN layers are distributed over the embedded CPUs available in the platform, and some of the CPUs offload computations on embedded GPUs available in the platform. Thus, in our approach, we take full advantage of computational resources available in the platform to ensure efficient and high-throughput CNNs execution on embedded devices. On this slide, you can see the design flow proposed by our methodology. It accepts as input a convolutional neural network, described as a CNN model, and a description of an embedded platform based on a CPUs-GPUs MPSoC. It produces an executable application that efficiently utilizes the MPSoC processors for high-throughput CNNs execution. Our methodology includes several steps. In the first step of our methodology, we explicitly specify parallelism available in the CNN. When the CNN is represented as a CNN model and executed by means of a deep learning framework, such as TensorRT or TensorFlow or ARM compute library, the parallelism within the CNN is specified by the deep learning framework and can vary for different frameworks. On this slide, you can see an example where two layers of a CNN are interpreted as two tasks by the TensorRT framework, but only as one task by the ARM compute library framework. This means that the CNN model does not explicitly specify the task-level parallelism available in a CNN, while explicit specification of task-level parallelism is required for efficient distribution of CNN workload on embedded MPSoC processors. Therefore, we convert the CNN model into functionally equivalent synchronous data flow (EDF) model. Unlike the CNN model, the EDF model explicitly specifies both task and data level parallelism available within the CNN. Moreover, it explicitly specifies communication and synchronization between the parallel tasks. We use the generated EDF model for the efficient mapping of CNN on embedded MPSoC processors. Under an efficient mapping, we understand a mapping where the CNN computational workload is balanced across all the processors available in the MPSoC, which means that the processors available in the MPSoC are efficiently utilized. Obtaining such a mapping is a complex design space exploration problem. To solve this problem, we propose to utilize a genetic algorithm, a well-known heuristic widely used to solve complex problems with large design spaces. To utilize a genetic algorithm for efficient mapping search, we specify two problem-specific genetic algorithm attributes, namely chromosome and fitness function. A chromosome is a string of special format that represents a problem solution. In our case, chromosome represents mapping of a CNN represented as an EDF model on embedded MPSoC. An example of a chromosome is shown on the slide. Every element in the chromosome, called a gene, represents mapping of a task within the CNN on an embedded CPU. Some of the embedded CPUs offload computations within the layers on GPUs. For example, second gene in the chromosome shows that CPU1 offloads computations on GPU1. As you can see from the chromosome, Only CPU1 offloads computations on GPU1. In our approach, we limit utilization of GPU resources so that every GPU has a specifically allocated CPU offloading computations on this GPU. Such limited utilization allows to avoid competition between the CPUs for the limited GPU resources. A fitness function is a special function that evaluates quality of solutions and guides the mapping search. In our case, the fitness function guides genetic algorithm for searching of solutions with a workload balanced across all the processors available in the MPSoC. This function is also presented on the slide. To find an efficient mapping, a genetic algorithm operates over a set of mappings represented as chromosomes. Such set is called an offspring. The first offspring is generated randomly. To improve the quality of the current offspring, genetic algorithm applies genetic operators, namely crossover, mutation, and selection, to the current offspring. During the crossover, two selected parent mappings exchange chromosomes to produce one child mapping. During the mutation, a random gene in the mapping chromosome is changed. During the selection, genetic algorithm selects a certain amount of the best chromosomes from the offspring. The chromosomes are evaluated by the fitness function. In our case, chromosome is considered to be of high quality if it ensures workload balancing across all the processors available in the MPSoC. The CNNs selected during the selection become a new offspring to which genetic algorithm applies crossover, mutation, and selection. The genetic algorithm runs until it reaches a certain number of iterations with no quality improvement in the offspring. When the efficient mapping is found, we derive final application model. The final application model is represented as cyclostatic data flow model, or CSDF model. The CSDF model is a more generic version of an ESDF model that we used for efficient mapping search. In our final application, every node represents part of the CNN computation executed on one CPU or one GPU. The generation of the final application is performed in two sub-steps. The first step is the partitioning of the CNN model, shown on this slide. In this step, the CNN is divided into subnetworks and distributed among the platform processors to form the CSDF nodes. Every CSDF node can contain one or more subnetworks. Every subnetwork is implemented by means of existing deep learning framework. For example, in our experimental section, we used ARM Compute Library framework to implement parts of the CNN mapped on the platform CPUs, and we utilized TensorRT framework to implement parts of the CNN mapped on the GPUs. A subnetwork can contain one or more layers and internal connections. The communication in synchronization within the subnetworks is performed by means of the deep learning framework. The communication and synchronization between different subnetworks is explicitly specified and implemented by means of the CSDF model and its first-in, first-out communication channels. The second step includes synchronization between the subnetworks mapped on different processors and having cyclic dependencies. Synchronization of such subnetworks is very important for preservation of the application pipeline. On the top part of the slide, you can see the CSDF model obtained after the CNN partitioning. You can see that actors A1 and A2 of the model have a cyclic dependency. Actor A1 expects actor A2 to execute input data layer, which provides input data for the convolutional layer of actor A1. At the same time, actor A2 expects actor A1 to execute convolutional layer to obtain input for the max pooling layer executed by actor A2. The important detail here is that on the top model, it is not guaranteed that the input data layer and max pooling layer executed by actor A2 will take turns while occupying the CPU resources. It might occur that, for example, input data layer is executed 3 times in a row, as it's shown on the right side of the slide. However, the efficient mapping generated by the genetic algorithm assumes that the subnetworks mapped on the same processors do take turns and are executed in a strict order, ensuring high CNN throughput. Inconsistency between the assumption adopted by the genetic algorithm and the actual CSDF model would lead to stalls or even deadlocks in the application pipeline. To preserve the application pipeline, we introduce phases into codependent actors' execution. The phases specify the order in which the subnetworks mapped on the same CPU or GPU are executed. For example, in the model shown in the bottom part of the slide, execution of actor A2 is split into phases that always follow each other in a strict order, shown in the right side of the slide. The bottom model is an example of the final application derived by our methodology. To evaluate our proposed methodology, we executed a number of real-world convolutional neural networks from the ONNX model Zoo on the NVIDIA Jetson CPUs-GPUs MPSoC. We compared throughput of the CNNs executed only with exploitation of task-level parallelism and implemented by means of the ARM compute library framework, CNNs executed only with exploitation of data-level parallelism and implemented by means of TensorRT framework, which is the best-known framework for NVIDIA Jetson MPSoCs, and CNNs executed with exploitation of both task-level and data-level parallelism as specified by our methodology. To keep the comparison fair, we did not apply any weights reduction techniques. The input data and weights are preserved in floating point precision. The batch sizes are preserved as they were specified in the CNN models presented in the ONNX model Zoo. As the experimental results show, our methodology allows to achieve significant higher throughput compared to the ARM compute library framework, which on NVIDIA Jetson MPSoC utilizes only task-level parallelism. And also, our methodology allows to achieve an average 20% higher throughput compared with the best-known TensorRT framework, which utilizes only data-level parallelism. As I mentioned in the beginning of my presentation, the presented research is conducted as a part of a European project called ALOA and received funding from this project. If you are interested in the project, please visit the links presented on the slide. In the end of this presentation, I would like to thank the organizers of SAMNOS conference for giving me a great opportunity to share my research. I would also like to thank everyone who is watching this video for your interest. I wish everyone to stay safe in these difficult times. If you have any questions, please use the SAMNOS website to ask them. Thank you for your attention.